Hi, my name is Brecken Liberty, and this is my presentation of the Lab 2 project on projectile motion. So for our simulation, our group created a simple drag included just simulation with an eraser where we threw it up in the air from right to left and let it fall back down to the table. And you can see in the top right, it shows the change in the x direction as time increases, and right below that is the change in the y direction as time increases. And the video itself shows the eraser going up, hitting a peak, and then going down, hitting just hitting the table and ending the simulation. So the glow script code is separate from the simulation we ran. The section 1 of this code creates time control. It defines drag, very importantly, as 0 and making it a gravity-only model. And then it sets up momentum, and it does a plethora of other things. Section 2, this is more where the code starts to become the graphs it's going to make, and that's going to be shown in the next slide. And section 3 rounds that out by ending the code and creating a few more graphs. And so that's shown here. This is all this is the culmination of the glow script code. Top left, you can see the actual video and image that was produced. Bottom left, you can see position versus time in x direction and velocity versus time in x direction. You can in the middle, you see position versus time in the y direction and velocity versus time in the y direction. And then in the bottom right, you can see a culmination of creating the trajectory of both x and y. So for the interpretation of tracker versus glow script, essentially the difference is gravity versus gravity plus drag. So in the gravity-only one, the eraser is treated as if the only force acting on it is weight, therefore making it F equals mg. And that creates a parabolic graph. In the glow script code, the program updates velocity each step based on the gravity and then updates position from that velocity. It ignores the effects of the air the eraser moves through, and that's a big, just not realistic whatsoever. So in the simulation we did, hence the second model, it improves the accuracy by adding air resistance. The net force is now F equals mg minus b, absolute value v times v, where the drag term opposes the velocity and grows with the square of speed. The constant b depends on factors like air density and the eraser's shape and can be adjusted to fit the experimental data. This shows that accounting for drag is essential for modeling the motion of lightweight objects like an eraser. So questions, what does it mean? Gravity only has no terminal velocity. The Vy just decreases linearly without bound. With quadratic drag, Vy approaches a constant Vt or terminal speed. The toss is likely too short to reach it. To measure Vt, give the eraser a longer drop, like a stairway or a balcony, or add area, like a parachute, so the speed levels off, and then estimate b for mg equals bvt squared. And then the what if question. With the same launch speed, throwing straight up takes longer to land than the angled throw because all of the speed becomes vertical, lengthening the ascent and total air time. This is true without drag. The flight time increases with vertical launch speed and remains true with drag. So conclusion, our experiment showed that the eraser's motion is not fully described by gravity alone. The gravity alone model reproduced a parabolic shape, but consistently overshot the measured range and peak height. Incorporating quadratic air and using tracker-derived initial conditions produced a close match to the experimental trajectory across the flight, confirming that air resistance is significant for a small, light object. The resulting fit implies a finite terminal speed, though our toss was too short to reach it. Remaining discrepancies likely stem from calibration and click tracking uncertainty, frame timing, and changes in the eraser orientation, essentially just human error. A longer vertical drop or increased area would let us observe terminal velocity directly and refine the drag constant for even better agreement. Thanks for listening to my Lab 2 projectile motion presentation. Thank you.